Swayam Prabha. Digital India. Educated India.
So we have been discussing common emitter amplifier. Let me recapitulate what are the important things we learned yesterday. Mostly we have covered simple C stage, okay, and we said we are going to cover the biasing today. So this was the simple C stage we covered in the last class yesterday. Okay, so let me recapitulate the important points we have covered. So this circuit was giving us gain which was GMRC with a negative sign 1 plus GMRE. Okay, and we said that we can, if this can leads to several conclusions. One of them was if we assume that GMRE much greater than 1, in that case this AV will be equal to minus RC by RE. Okay, and we said that is gain is independent of transconductance of BJT. Okay, second we just let me see once more. Am I yeah, okay, that's fine. So yeah, so that was one conclusion we made. There can be other situations. For example, if we divide with GM, we are getting AV equal to again, this is an important important equation which shows that the gain in the numerator it is the resistance associated with collector, and in the denominator it is 1 by GM. That's the resistance looking from the emitter side when your base is AC ground, and also it is plus the resistance which we are adding in the emitter. Okay, so this was the second important result we get, and we also mentioned that this equation shows that gain is AV is less than GMRC, right? If we use RE, okay, and that can be minimized by adding a bypass capacitor. Okay, bypass capacitor. So bypass capacitor across RE. Okay, and if I do that, then we will have AV is equal to minus GMRC, as if RE is not there. Okay, but RE plays a very important role. That is, we mentioned that RE will stabilize biasing. Okay, and it also increase input resistance, and the input resistance Rin now is R pi plus beta plus 1 Re. Okay, so this is again an important relation, because if you remember this, because then whatever you connect at the emitter, that will be basically reflected beta plus 1 time when you look from the base side. Okay, so this part we have covered in the last class yesterday. We have also then extend this discussion and said said if we have additional resistance Rb, which which will reduce the gain of the circuit, we mentioned. Okay, but sometime it is unavoidable and we have to use this resistance which is connected to the base, right? And we because the gain will reduce, because some part of V in then will be across Rb. Okay, so we will have a resistor divider circuit where there is Rb, there is R pi, and also there is beta plus 1 Re. Okay, that is we discussed yesterday, and that will ultimately reduce the gain. And interestingly, we got a relation which is similar to what we get what we have what we get here. Okay, similar to this relation. The only difference is there is an additional term which is let me write it down. So without Rb, this was the gain equation. Okay, and the additional term is this, which is coming because of this Rb. Okay, although this effect might be less if the Rb value is less, because you see it is you are dividing Rb with beta plus 1. Okay, so it can be this beta plus 1 can be a couple of hundreds, and this effect might be not much. Okay, we have also mentioned that this will change the input resistance, although your one of your friend then pointed out like which input resistance we will be interested in, because there are two input resistance we mentioned, and this is your Rc and this is your Re, and I said like there is R in 1 here, and also because of Rb this voltage source will see another resistance which is R in 2. Okay, whereas R in 1 is known to us already, that is R pi plus beta plus 1 Re. Okay, whereas R in 2 will be Rb plus R in 1. Okay, I can confirm that R in 1 is the most important one, because that is the actually the input resistance from when you look here. Okay, however this voltage source will see this total input resistance. Okay, along with its own resistance, it will see this is basically the core input resistance of that amplifier circuit. So this part, up to this part we have discussed, although this R out will remain the same, that is Rc. Okay, now we haven't so far we haven't considered the effect of R naught that much. Okay, so effect of R naught, that is effect of early voltage in this output resistance calculation. Okay, so if we have like okay, so that's basically R out, and I am considering the effect of R naught. Okay, so if you consider effect of R naught and try to find out R out, then you can you remember we have to apply a test voltage at the output, whereas we need to short the input side, right? So if you do that, we have done this before couple of times. So the circuit can be drawn like this, where we will now have R0. Let's for the time being not considering RC, just R0, and also we are not considering RB, which we have discussed just now. Okay, so this is your Vx, this is your Ix. Okay, so again what we are aiming at, what is the value, what is the effect of R0, that is the output resistance which occurs because of early voltage. Okay, so sorry, so this you need to ground. Okay, input side you need to ground it, and this is the so this Ix is entering from here, and you see Ix will be divided into two parts. One will go through R0 and the other part is basically GM V pi. Okay, so they again mix and form Ix. They again mix and form Ix here, right? I hope that is understandable. Now you can redrawn the circuit even further, just to so I am redrawing it once more. You see, so that it will be easier to visualize. So I hope again this is self-explanatory. I have just you see, because this is this point here, we can just because you see R pi and Re is basically parallel. R pi and Re is basically parallel because R pi is grounded. Okay, and R pi here is connected to Re, so these two are parallel. Okay, and Is are entering here. So I can now calculate. So all I have to do, I have to find out an expression for Vx over Ix that will basically give me R out. Okay, so we have to find out this expression so that we can get the expression of R out. So we can write V pi is equal to minus Ix R pi. This is Re. Okay, the minus sign is there because you see the polarity of V pi, negative up and positive down, right? Whereas the Ix is entering from top here. Okay, so this should be a negative sign, right? So we can write V pi like this. Okay, and as I mentioned, Ix is the current through R0 is basically Ix minus GM V pi, right? Because one part of Ix, that is GM V pi, so other part is basically going through R0, right? So we can write Vx is equal to Ix minus GM V pi into R0, that is the voltage drop across R0, plus minus V pi. Okay, because V pi is opposite polarity. So Vx, this voltage is divided in two parts. One is across R0 and the other part is basically V pi, because V pi is because R pi and Re is in parallel, so V pi is voltage drop here. Okay, so and that will be of negative sign because the V pi polarity is opposite, right? So you can put this V pi expression here, and okay, so I just put V pi expression, that is minus Ix R pi Re here, all these two V pi position, okay, and this is the expression I get. So I can readjust this and end up with R naught plus Gm R naught plus 1, okay. RE parallel RE parallel R pi, this is RE parallel R pi, right? Sorry, okay. So and this is basically your R out, okay, this is basically your R out, because you can take Ix common here, and Vx over Ix is basically R out, and this is R naught plus Gm R naught plus 1 multiplied by Re parallel R pi, okay. So if you now let me write it once more, the last line of the previous slide, that is R naught plus 1 plus Gm R naught Re parallel R pi, okay. Now often Gm R naught is much greater than 1, and then this R out will be nearly equal to R naught plus Gm R naught Re parallel R pi, and you can take common this R naught, so you see because of this degenerate emitter, because of this Re, okay, because of this Re, this additional term has occurred, okay, otherwise the R out will be R naught, okay. Now this additional so the R out now becomes multiplied, this is the multiplication factor 1 plus Gm Re parallel Re parallel R naught, okay, Re parallel R pi. So that's the multiplication factor, okay, which is appearing because of the Re, okay. Now we can have two cases. Case 1, where if we assume that Re is much greater than R pi, okay, if we assume Re much greater than R pi, so if that is the case, then Re parallel R pi will be nearly equal to R pi, right, because we are assuming Re much greater than R pi. In that case we will have R out equal to R naught 1 plus Gm R naught, okay. That is we can say sorry, so that is we can say equal to beta R naught, right, because Gm R pi is beta, okay, and beta 1 plus beta, we are just writing beta, okay, beta R naught. So you see the R out value now is a you have to multiply that R naught with beta to get R out, okay. However case 2, where if I assume that Re is much less than R pi, in that case Re parallel R pi will be nearly equal to Re, okay. So your R out will be equal to, okay, R naught 1 plus Gm R pi, 1 plus Gm Re, sorry, okay. So then the boosting factor is 1 plus GMRE. So depending on the value of RE and RPi, someone in the last class asked me what if we consider the effect of early voltage, then your output resistance is going to vary. The output resistance will be equal to beta R naught if RE much greater than RPi, and if RE much less than RPi, R out will be nearly equal to R naught 1 plus GMRE. Okay. Now, so I thought I will stop here. Just to mention one, sorry, and similarly you can find out gain and all that. You can consider the effect of RC. When you consider RC, what will be the relation and all that. I am leaving it up to you. Okay, so you can do that, I hope. So just an example I would like to put. Again, this is from Rajavi's book. You see, I have two transistors Q1 and Q2, and I want to see R out if I have this configuration. Okay, where the voltage is connected to the base of Q2. Okay, so what you can do, you can replace this if you think carefully. This particular type of arrangement where one transistor is on top of another in the form of stack is known as cascade. You will probably come across several times after this because cascade we use heavily for designing current source and all that, current source or current sink. So this can be replaced by, if you think carefully, this can be replaced by RO2, this bottom transistor. Okay, because you see this is DC, this is connected to a DC supply. So this GM2 V2 GM2 Vpi2 can be considered 0, and you can replace that with RO2. In that case, your R out, if you look from this side, will be the same what we have, what we just now calculate. Okay, so that's basically your as if your RE. Okay, that is your degenerate your degenerate emitter. Anyway, so what we again, this example is from Rajavi's book. You can just see the example in little bit more detail. It is done over there. So let's now discuss what we mentioned in the last class, that so far we haven't considered any biasing situation. However, we need biasing circuits so that the transistor remain in forward active mode when it is performing as an amplifier. Okay, so now what we will consider, C stage with biasing. Okay, let's assume the simplest case of biasing. You remember we have simplest case of biasing we have discussed, that is single resistor biasing. Okay, right, this was the single resistor biasing circuit, you remember, and this is RC, this is RB, so on, and we mentioned that the usually RB value is quite large, so that the this base current is a small, okay, of the order of microamp, and this is usually mega ohm and so on. So this is the single resistor biasing which we have discussed before. Okay, what I try to do, I try to add a AC signal. For example, say microphone, okay, because we have been taking considering microphone at the input and speaker at the output and so on. Anyway, you can consider a small AC source with tiny resistance associated with it. Okay, I will put some values just to show you one particular issues with this circuit. So we want to amplify this microphone signal at the output here. Okay, and so say this is 100 kilo ohm. Okay, this is say 1 kilo ohm, and this is say 2.5 volt. Okay, now if you use this circuit, you will find that this circuit is not working properly. Okay, why it is properly? Say this is position X. Okay, so why it is not working properly? If I calculate my DC voltage here, okay, considering say the resistance associated with this microphone is say 100 ohm. Okay, so then this base emitter voltage, this X Vx, that is basically will give you the base emitter voltage, right? Vx we can calculate. Okay, and that is like 2.5 millivolt. Okay, so you see one important aspect you always remember, which we haven't discussed before probably in this explicit form, is if we apply any AC signal at the input of an amplifier, we always have to use a capacitor. Okay, what this capacitor will do, this capacitor will basically isolate your AC signal from your DC signal. In other words, what this capacitor will do, it will not it prevent the AC signal to change the DC biasing. Okay, so if you can add a, so this is your microphone signal, you can add a capacitor. Okay, which will basically you choose a value in such a way so that the capacitor impedance is almost short for your AC signal. Okay, that is omega 1 over omega c is almost short, whereas it is open circuit for the DC signal. Okay, that way you will manage to keep your Q point intact. Okay, here you see your Q point is gone because the transistor is this transistor is off, because transistor has to have 0.7 volt at the base emitter. Okay, and because of this AC signal, because of this microphone which has very small input resistance associated with it, it's basically bringing down the base emitter voltage. Okay, so all you have to do, you have to choose a capacitor carefully so that your AC signal will pass through that capacitor. For the AC signal frequency, it is a short, whereas it is isolating this AC and DC signal. Okay, so that your Q point will remain intact. Okay, and we know if we just draw the DC circuit once more, just for your recapitulation purpose, say this is your Y and this is your point X. Okay, this is your RB, RC, this is VCC, and this is just the DC supply, DC circuit. Okay, then this is your point Y, this is Q1. Okay, then of course DC current, DC I mean collector current, we can obviously write this way. This is we have written before. Okay, so VCC minus VBE over RB is basically your IB. Okay, DC current, and multiplied by beta is basically your IC, and we have to make sure that this is in the forward active mode. Okay, that we can that will be ensured if we choose this, right? So Vy is obviously, that is the VCE. We already know that will be VCC minus ICRC. Okay, and IC is this, so you can put IC here. Okay, that into RC, and this should be greater than VBE or Vx. Okay, that will ensure this is in the forward active mode. I think this part we have discussed before. So what about our what about the effect of this RB, this biasing resistance on the gain, okay, or on the input resistance, that we need to figure out, right? So that is again can be done very easily if we just redraw our circuit. Okay, considering the,
can you show the previous page?
Yeah, yes. So in the previous page, all I have done, that I discussed two issues. One is you have to include a capacitor so that you can isolate AC signal from the DC signal, and that will ensure your Q point remains intact. And then what I did, like this is the condition you needs to be there, so that your transistor in the forward active mode, that is the voltage at the collector VCE should be more than equal to of VB or Vx. Okay, and that this voltage can be written as VCC minus, so this is basically, this is nothing but VCC minus ICRC. You see, this is pretty easy, ICRC, and IC you can write beta beta IB, and IB is basically this. Okay, so so then we can redraw the AC small signal circuit. Okay, I'm not drawing GM, pi and all that. That is there. Okay, what I am aiming at is, like you see, RB will be grounded if you think about AC signal, and also RC will be grounded. The reason RB will be grounded, because RB is connected to VCC DC voltage, and that DC we need to ground, right? DC is basically AC ground, so we have to ground the other part of the RB, and one part is we know connected here. We are shorting this capacitor because we are talking about AC signal, and there will be, we can always replace this transistor and say there is R pi, GM, V pi, and the emitter is grounded, and also RC, one part is connected to your collector, that is V out, and other part is grounded because that was connected to your capital VCC. Okay, so again you can find out V out over V in, that is gain, that is nothing but minus GM RC. You see, because you see here V in RB is parallel, so V in is basically the same voltage is coming at the base of the BJT. Okay, so RB doesn't have any effect as far as the as far as the gain is concerned. Okay, of course you can consider R naught, and in that case if you consider your early voltage is less than infinity, in that case obviously your gain will be minus gm RC parallel R naught. This part we have discussed before. Okay, what about your input resistance? Okay, again your input resistance you can divide like we did before. So your so your input resistance will be you can again write R in 1 and R in 2. Okay, so you can see R in 2 will be equal to R pi parallel RB, right? Because RB you see now in parallel to R pi. If you just change this transistor, then you will see that RB is coming to parallel of R pi. Okay, so that is why this input resistance is going to change, and depending on the value of RB, the net input resistance will be lowered because of this biasing resistance. And what about R out? R out obviously equal to R naught parallel RC. Okay, so another important aspect I would like to discuss before I finish today's class. So that is, say this amplifier is delivering the power to a speaker. Okay, we are taking the signal from a microphone and it is amplifying it, this common emitter amplifier circuit with a single resistor biasing RB, and then it is basically delivering the power to a speaker. Okay, so if I do that, okay, so this is my DC biasing circuit. I have this capacitor, okay, coupling capacitor, and I have now a speaker here. Okay, or right, let's assume the speaker resistance. I think you have that example which we will discuss at the beginning of this amplifier class. The speaker resistance is say 8 ohm. Okay, speaker resistance is 8 ohm. Now if you use this circuit, you will find the circuit is not working. Okay, the reason it is not working, simply because this resistance which is associated with this speaker is so low that it simply bring this transistor to saturation. Okay, in other words, this speaker, again I have to isolate from this core circuit so that its Q point remains intact. Okay, since this speaker resistance is very low, it will make VCE too low. Okay, it will almost short your VCE. So that way its biasing will be lost. So what we have to do, again the same thing I am telling you, is you have to isolate both your source and your load. Okay, from your core biasing circuit through coupling capacitors. Okay, so now you see your from the input side it is not hampering your biasing, from your load side also it is not hampering your biasing, right? So that way you remember always you have to connect these kind of coupling capacitors. You have to carefully choose the value of coupling capacitors so that it is almost short for AC signal, whereas of course it will act as an open circuit for the DC signal, so that your Q point remains intact even if there is lower resistance or impedance associated with your source or your load. Okay, now even if you do that, you will find this circuit is not working. Okay, the reason being your gain of this circuit, even if you capacitive couple this circuit, your gain is, you remember, RC parallel your, say this is your RL. Okay, and your RL is very tiny in this case, so it will reduce the gain drastically. Okay, it will reduce the gain of the circuit drastically, so you will find that you will not getting any sort of any gain probably out of this circuit, although it is used for for amplifier circuit. Okay, for amplification purpose. So what you should do, one way of doing that is one way to get proper amplification out of this circuit, which will not be deteriorate because of your value of your load, is to use a thing called buffer. Okay, you will come across buffer later on. Okay, so we have to use a buffer circuit. The purpose of buffer circuit is to so we have to apply kind of buffer circuit. What is buffer circuit we will discuss later, but buffer usually have high input impedance or high input resistance and low output resistance. Okay, so that way it basically isolates it can isolate input and output. Okay, so that way you can improve the situation, and that way you can get a good amount of gain, or the gain you are looking for, because here the input resistance is very high, whereas the output resistance will be low, and that way you will be able to achieve your amplification. Now the last part, just for 2 minutes, what I want to mention is second case of biasing, which is voltage divider biasing. Okay, this we will discuss in more detail tomorrow. Voltage divider biasing. Okay, you remember we discussed this before again. So this was this is voltage divider biasing circuit, where we have two resistors R1 and R2. We have VCC, and of course we need a coupling. We need a coupling capacitor. Okay, and just for the time being, I am assuming that there is no degenerate emitter, so there is no resistance, or emitter is directly shorted to ground. Okay, and tomorrow we will discuss what will happen if we connect that RE. Okay, so you can basically redraw this circuit to get more insight. For AC signal, what will happen when we think about only the small signal amplification? Okay, you see we can reduce the circuit on the left hand side. uh, right, because you see VCC is AC ground, so your RC will be grounded at the output, that is obvious, and also your R1 and R2 will be connected to base one terminal and the other terminal will be grounded, right? So, and of course we are considering that capacitor is shorted for the AC signal. So if we use that, you see your Rin, okay, will be equal to R pi parallel R1 parallel R2, right? Your Rin will be R pi parallel R1 parallel R2, and your gain, okay, gain will be the same, because sorry, minus RC over 1 by GM plus RE. Okay, because you see that sorry, this RE I am taking, I should have discussed this in the in tomorrow's class. So your gain will be just GMRC. Okay, sorry. So RE will come into picture if when we take RE into account. So your GM, your gain will remain the same. Of course, your Rin will deteriorate a bit depending on the value of R1 and R2. Okay, and so this and of course R out will remain the same. Okay, R out will remain the same. So this is your voltage divider biasing, where because of your R1 and R2 your input resistance will deteriorate a bit. Your gain will remain the same because this Vin is not changing, because this R1 R2 in parallel with this Vin. So this Vin voltage will come at the between the base and emitter, and your gain will remain the same, your output will remain the same. Okay, output resistance and your input resistance will deteriorate a bit. So we will discuss tomorrow what will happen if we connect RE here. So today we are closing this class now. So if you have any queries, you can ask me. Okay, please raise your hand and then we can take few questions.